Oh, you can see that I move slides.
Yeah, I
Okay.
can see.
So thank you for your introduction and for the opportunities to speak here. Good afternoon. In my talk, I will discuss the fluctuation response relations, so the novel relations between the fluctuations and current responses in Markov systems. And so both exact identities relating the fluctuations and responses and the bounds on responses in terms of fluctuations. And the work was done in cooperation together with Timur Asyamov and Massimiliano Esposito. It was published in 2 papers, and actually Timur was the primary author of the second paper of Q-synchron identities. And I work at the Institute of Molecular Physics of the Polish Academy of Sciences. So, as I said, the main result of our work is concerned with the novel relations, both identities and bounds relating the current responses and fluctuations in Markov jump processes. And in my talk, I will first present the motivation of our study, so the equilibrium fluctuation response relations. And then I will briefly review the formalities of Markov jump processes. I will also review the previous results on thermodynamic uncertainty relations. And then I will present our results, namely the fluctuation response relations, which are valid far from equilibrium, and as well as a certain band that follow from that relations, which is response TUR, response thermodynamic uncertainty relation. And finally, I will present some applications of our results to thermodynamic and model inference. Okay. Okay, so as we probably know, when we consider systems at equilibrium, then we can see that responses and fluctuations are related to each other by the laws of thermodynamics. And an example of such relation is a famous Einstein relation, which relates the ordered movement of the particle to the random fluctuations. Namely, we know that the particle in the viscous medium can undergo both the ordered motion induced by some external force, but it also undergoes random fluctuations called as Brownian motion. And the Einstein relation relates the diffusion coefficient, which describes the rate of growth of the mean space displacement of the particle from its average position to the Brownian motion, to the mobility of the particle, which is the response of the velocity of that particle to the applied force, and the proportionality constant between the diffusion coefficient and the mobility is the temperature multiplied by Kb. So we can ask ourselves a question whether there is some similar relation which can relate the fluctuations and responses arbitrarily far from equilibrium. And is also related to the question whether actually the laws of thermodynamics limit somewhat the ratio of the response of the system current response to fluctuations, as thermodynamics relates the fluctuations to response at equilibrium. So in our work, instead of a movement of the particles, which is generally described by some form of Langevin equation, we rather focused on Markov jump processes, which describe stochastic jumps between some discrete, within some set of discrete states of the system. And there are many examples of physical systems which can be described by Markov jump processes. For example, the dynamics of quantum dots can be described as in terms of stochastic jumps between charge states of the quantum dot, which are induced by tunneling of electrons between the quantum dots and the applied electrodes. Similarly, many chemical systems, such as molecular machines, can be described by Markov models. And for example, the dynamics of the molecular motors can be described in terms of stochastic jumps between the different conformations of this molecular motor and different chemical states. And for example, such Markov jump processes can be also used to describe like matter interactions in the limit of applicability of Pauli-Master equation. And generally, dynamics of system described by Markov jump processes is described by Markov rate equation, which describes the dynamics of probabilities of different discrete states of systems. And such probabilities are increased due to the jumps from other states of the system and are depleted by the jumps from the considered state to the other states. And this equation contains the transition rates WAJ, which describe the rate of transition from the state J to the state I. And also, often one wants to resolve between transition to different reservoirs induced by different reservoirs, because, for example, in a quantum dot, the same transition between empty occupied state can actually correspond to two different physical processes, either tunneling from left dot or from the right, from the left electrode or the right electrode. And therefore, we introduce also the index nu, which describes the reservoir which induces the transition. And we also know that in Markov systems, one can observe notable fluctuations of the observed currents. And to characterize such fluctuations, one introduces a certain stochastic charge denoted Q, which may, for example, in quantum dots correspond to the electric charge transferred to some electrode. But for example, in the case of single molecule, it can just correspond to the particle displacement from the initial position. And indeed, such a stochastic charge can be measured experimentally. For example, displacement of the molecule from the original position can be measured using some optical methods. And this charge is stochastic quantity, so it is defined for a single stochastic trajectory of the system during some interval 0t. And based on this stochastic charge, one can define the average current of the system, which is just the average charge divided by time. And we consider the limit of time going to infinity. And this average here is average over stochastic trajectories of the system, which in experiment may just correspond to average over different experimental realizations of the observed process. And also using this stochastic charge, one can also define the current variance, which is just the average square of the displacement of this stochastic charge from the average value of the stochastic charge. And this mean square displacement is scaled, so it is so like the current it's also divided time, and we also consider the stationary fluctuations, so we take the limit of time going to infinity. And it is known that these quantities, so both the average current and the current fluctuations, obey so-called thermodynamic uncertainty relation, which states that the ratio of the average current, which is squared, divided by current variance, is bounded from the above by the entropy production divided by half. And the entropy production, as we probably know, is a key measure of thermodynamic irreversibility. It generally can be expressed in terms of heat exchange with different reservoirs, multiplied by heat currents to different reservoirs, multiplied by weights, which are just the inverse temperatures of these reservoirs. And this thermodynamic uncertainty relation has two implications. On the one hand, it shows that dissipation can band precision of current, which we often want to optimize, and the precision is defined as current as a ratio of the current to fluctuations. So to increase this precision of current, one needs to increase also dissipation in the system. And on the other hand, it can be used for thermodynamic inference. So one can infer the value of the entropy production, which is usually unknown, directly just by measuring the average current as well as current fluctuations. But in our work, instead of just currents, we considered the current responses, and in particular, we focus on static responses of the current. So let us define those static responses. So in our work, we always consider non-equilibrium steady state of the system, in which the probabilities of different states stay constant, they do not evolve. And we define the average current as the steady state current for a given value of some control parameter P, which generally controls the transition rates in the system. And the static response we consider is just the difference between the current value, steady state current value from for a slightly perturbed value of this control parameter minus the original value of the steady state current divided by the magnitude of the perturbation of that control parameter. So from operational perspective, it corresponds to situation when we first measure the original current for the original steady state, then we slightly perturb the system, slightly perturb this control parameter P, and wait a long time so that the system relaxes to the new steady state, and we measure the current for the new steady state. So we don't consider dynamic responses of the system, only steady state responses. And then to define our result, we further parameterize transition rates, which were previously expressed in terms of initial and final state and the reservoirs by means of single index E, where the index plus E corresponds to the transition from the state J to the state I for a given induced by given reservoir nu. And the transition W minus E, transition minus E corresponds just to the reverse transition, but induced by the same reservoir. And we then parameterize transition rates W plus minus E in terms of two parameters. One parameter BE describes kinetic barriers between different states, which, for example, may correspond to the tunneling barriers in quantum dots or activation energy in chemical systems. And this and the sign of this term does not depend on the sign of E. And the second term is entropy flow to the environment, this term SE, during the jump plus minus E. And this second term is related to thermodynamic forces acting on the system. And our first main result, which was actually the second result, but chronologically, but I think it is better to present it first, is the fluctuation response relation, or the fluctuation response relations, which express the value of the current variance in terms to current responses to either the perturbation of the kinetic barriers or this entropy flows, and this is given by weighted sum of these responses with the weights which are expressed either by terms of edge currents, so the probability currents associated with each transition E, and also in terms of edge traffics, which quantify the rate of transition in both directions of the transition, so both the direction plus E and the direction minus E. And these such relations are valid arbitrarily for far from equilibrium, and we believe it is one of the first results which directly relates the fluctuations and response only in terms of quantities which are in principle measurable. And this identity has some further consequences, namely using the Cauchy-Schwarz inequality, one can derive new inequalities which result from this equality. And one particular interesting band is the band we call response TUR. And it is applicable to the situation when we consider a so-called kinetic perturbation, namely the perturbation in which some control parameter affects only the kinetic barriers but leaves the thermodynamic forces unaffected. And there are many examples of such perturbation in physics. For example, in an electronic transistor, the gate voltage controls the conductance of that transistor, but does not affect the thermodynamic forces acting on the transistor, which are only determined by the voltage between the source and the bias of the transistor. And also, this kinetic perturbations describe the influence of weak magnetic fields of chemical reactions because thermodynamic potentials are not affected by weak magnetic fields, but weak magnetic fields may control the kinetics of chemical reactions by influencing the singlet-triplet interconversion rates, and such effect is hypothesized to play a role in navigation of birds in Earth's magnetic field. And the result we obtain is that the response of the current to this control parameter epsilon, which is squared, divided by the current variance, is bounded from above or by entropy production divided by 2, but also multiplied by some factor Bmax squared, where this Bmax corresponds to the maximum rate of change of kinetic barriers due to the modulation of this control parameter epsilon. And it is very similar in idea to standard TUR, standard thermodynamic uncertainty relation, but now bounds not the current precision of the current itself, but the precision of the current response. And this band shows that to obtain such a response of current to kinetic perturbation, we must pay some thermodynamic cost, which is quite intuitive because at equilibrium there is no current, so also there is no current response to kinetic perturbations. And finally, let me discuss some application of our results. And the most intuitive, let us say, application may be thermodynamic inference. So as I defined before, this inferring the value of the entropy production given based on measurable quantities. But it is actually not so easy with our band because it includes the parameter Bmax, which actually depends on the model. So we cannot actually, with our band infer the entropy production using only measurable quantities, given no knowledge of the model. But we can relax our assumptions, and we can define thermodynamic inference as a task of inferring the entropy production using empirical data, but without the full knowledge of the model, but having some partial knowledge of the model. And then we considered them as an example, we consider the molecular motor composed of 3 states. It is some idealization of the molecular motor, in which one of the transitions is controlled by concentrations of chemical species F and W, which may, for example, correspond to ATP and ADP. And we assume that we know the structure of the Markov network, that it is the 3-state system. And also we know something about this transition 1, namely that is given by some mass action law, with the transition rates being proportional to the concentrations of species F and W multiplied by some reaction constants. But we also assume that we don't know reaction constants, and also we don't know the other transition rates in the model. And then we can express the response of the current to the kinetic barrier at the first transition only in terms of measurable quantities using the chain rule for derivatives. So we can express this response in terms of a response of the current to the concentrations of species F and W, and such responses are now measurable. And then we can actually band the value of the entropy production from below using only measurable quantities, namely the current fluctuations and the response of the current to the concentrations of the chemical species. And the second application we discuss is the model inference. So getting some knowledge of the about the microscopic model of the system given measurable quantities. And for this task, we can use the bands on linear responses of the system which follow from our result. Namely, such bands are applicable close to equilibrium when the linear response of the current to the applied conjugate force, for example, when we consider the electric current, then the conjugate force is the voltage. And then close to equilibrium, such response is just equal to the current variance divided by 2 by means of fluctuation dissipation TR. And we now consider a kinetic response of such a response. So again, consider a situation when some control parameter controls only kinetic barriers. As an example, we can consider how the electric conductance of the transistor close to equilibrium reacts to the applied gate voltage. And we have shown that the linear response coefficient describing the response of the current to force, namely the response of the response obeys is bounded from above by the response coefficient itself, and this our coefficient B max, which describes the maximum response of kinetic barriers to the controlled parameter epsilon. And therefore, using only measurable quantities, that is the linear response of the current to the applied force, and how it is modulated by the control parameter which controls the kinetic rates, we can infer the value of this parameter B max, so which is microscopic parameter because it describes how transition rates in the model respond to the control parameter, and therefore we can gain some knowledge about the microscopic physics from the model, from the macroscopic measurements for a given system. And to conclude, in our work, our focus was were the responses of steady-state currents to perturbation of transition rates in Markov jump processes. And we demonstrated both the fluctuation response relations, so the exact identities which relate the fluctuation to current responses, and also obtained novel bands such that the response TUR, which bands the precision of responses of currents to perturbations which affect only kinetic barriers of the system. We also generalized this result not only to current variances, but also the current covariances, as well as to covariances between time-integrated state observables, which were discussed today in the presentation of Eugene Kwon. And actually, Eugene Kwon with co-authors also generalized our response to QR to the case of transient dynamics. So we now know that this band is not only applicable for static responses at this state, but also in the transient regime. At this point, I would like to thank you for your attention and also invite you to ask questions.